Thank you very much. Good afternoon, everyone. It's great to be here. I'm James. I'm a DevOps lead at Nominet. You probably heard of Nominet. We are, amongst other things, the .uk domain registry. So if you own .uk domain or are in businesses who own .uk domains, you've probably interacted with us in some capacity. We also run GTLDs. So for example, .audible, .comcast, .gucci, and perhaps slightly closer to your own hearts, .IEEE. Alongside the registry business, we also run protective DNS, so cybersecurity solutions for governments. So this afternoon I'm talking about networking and Kubernetes. I don't know any of you, I don't know what your backgrounds are, so we're going to start with an introduction to containers and what containers are, why they have sort of sprouted out into Kubernetes, and then we'll get on to the actual networking piece. I'm not a networks engineer, but I'll do my best. Please be kind to me, and hopefully we can have some interesting discussion if I'm, you'll see what I say. So firstly, what are containers? So containers are a way of packaging and distributing software. They are runnable. They are. You may well have heard of Docker. You may well have run Docker containers on your laptop. I remember I think it was 6 or 7 years ago, first coming across Docker myself and trialing bits of software. And it was the first time I'd trialed bits of software and found it dead easy because I was running a Docker container on my laptop rather than having to sort of interact with the native package manager and actually fully install the software. So containers are runnable. They are portable. It's not just a bunch of files. They're designed for distributing code and helping you to run them in lots of different places. And one of the reasons they've become popular is that developers can run them just as easy on their laptops as an ops team can then help run them in production context. Containers are also secure. Now, no system is ever secure. The fact there's a system means there is a security issue. But compared to a virtual machine running the same application, a container is a trimmed-down operating system. It has, therefore, a reduced attack surface and can, therefore, be considered more secure. Sorry, I'm just trying to get our notes to stop scrolling the wrong way. There we are. Containers are run from immutable images. So one of the benefits of this is that developers can work on their images and build them, and then they can be certain that when they get deployed into a production setting, that what is run is what they intended to run. It's what they actually built and designed to run. And they are built from layers. One of the great things about this is they are quick to distribute and quick to start up at runtime. So on the left-hand side of the diagram there, we've got a container represented as a very glamorous square cubic blob. If we think about what the layers might be that comprises the container, we've got a mini operating system as the bottom layer, some application libraries as the middle layer, and then the application itself as the top layer. This is obviously a very simplified example. So just to put some meat on the bones, we might have Ubuntu as our bottom layer, a web server as the middle layer, and then the files comprising the website as the top layer. So that's containers. How are they run? So containers run using a container runtime interface. That's probably pretty obvious just from the semantics of those three words. But the runtime interface is there to basically give the container access to underlying resources that it needs. So, for example, CPU, RAM, disk, and network. So you can run a container runtime interface on your laptop, for example, Docker. But obviously in the kind of production setting, enterprise setting, we're thinking about running many containers across many computers, many servers, and this is because we're distributing or running our own application stack, and we're interested in things like redundancy and resiliency. So enterprise systems, as alluded to in the previous talk, comprise many components, many microservices in many businesses. We want lots of replicas running. For example, we want at least 2 replicas of everything running behind our load balancer. And so this kind of presents us with a new problem. We've got these containers, and that's great, but how do we actually run them in a way that's any better than just distributing our software onto a bunch of servers? So in order to do that, we need an orchestrator. This allows us to run many containers across many servers. I think it's clear from the way the industry has gone for a long time that Kubernetes has been the kind of de facto orchestrator. And what Kubernetes gives us is a kind of brain that sits at the middle of our cluster, the heart of our cluster. A cluster just being a bunch of VMs that Kubernetes controls, typically referred to as nodes, and it gives us some of those desirable features that we need for running enterprise-grade systems. So resiliency, redundancy, self-healing, portability. All the major hyperscalers have their own flavor of Kubernetes that you can interact with. And then we have virtual networking, which gives us a lot of flexibility compared to a traditional estate, which comprises kind of just a bunch of VMs. I've recently tried to put... Oh, sorry, that was clearly the wrong... There we are. Right. Sorry, I've recently tried to describe Kubernetes in 8 S's as kind of a bit of play on the words, play on the abbreviation. I've also played with the logo for those of you eagle-eyed. So Kubernetes is a scheduler. This is just another word for orchestrator, so it exists as that brain that is going to schedule containers onto our available nodes. That is basically compute, where the workloads can actually run. Kubernetes is a state machine. It's designed to maintain state. If a node falls over due to some underlying hardware issue, the containers will be recreated somewhere else. And so Kubernetes, the brain, the scheduler, is maintaining state. It's a state machine. We interact with it as developers, as application or operations teams by deploying sets. So a set is just when we tell Kubernetes we want at least 2 replicas of this application or that application, and please go and maintain that state for us. That is the set that you need to deploy for us onto the available nodes. Services are, we'll talk in more detail about later, but this is one of the kind of fundamental networking features of Kubernetes, and it's how it exposes our sets of applications to allow load balance access, and perhaps building up that kind of microservices graph that Giles showed us in the previous talk. Storage. You might think of Kubernetes and containers as lending themselves to stateless applications, but it also has storage APIs allowing us to interact with storage and do stateful things. Kubernetes is secure. As I said earlier, no system is secure. How dare I say that? But it has, I think, security at its heart. It's taken very seriously, and features such as encouraging us to not run containers as root, running our containers with an immutable file system. These are at the heart of what Kubernetes is encouraging people to do as they run their application stack on it. Kubernetes is stable. Again, how can you say that of anything? But I think certainly if you dig into how it's built and tested, it is designed to be run at scale. It is run at scale by big companies around the world, and the core components are performance tested to ridiculous extent. And finally, it's simple. I think I wanted to put standardized here. I was sort of toying with what word to use, but one of the advantages of Kubernetes, although this is never going to be perfect, is you can move your workloads from an on-premise, perhaps an open source deployment, into one of the hyperscalers, a cloud-based deployment, and you can interact with it using the same API. So for developers, for DevOps teams, or whoever it might be is actually responsible for running things on Kubernetes, you could argue that it's simple compared to previous worlds. So that brings us on to Kubernetes networking. So the blue box here represents a cluster, which is kind of our typical unit of what one Kubernetes brain can control, one Kubernetes control plane. And on our cluster, we've got 4 worker nodes. These are just either VMs or bare metal hardware that's going to run our containers at the end of the day. And then on each of those nodes, we've got some containers, although these are more typically referred to as pods, with some slight semantic differences when in the how Kubernetes refer to them. I won't go into more details now. And from a networking point of view, we have 3 networks to consider. There's the kind of physical network or the host network, and I've just given dummy private blocks to each of these to highlight that they're completely separate. So these are just this is the underlying network that the VMs or the hardware is connected to. And then you've got the pod network, and this is we'll get into more details, but it's basically a way that the pods can communicate with each other. And then we've got the service network, which isn't really a network at all, so we'll get into more detail on the next slide. So the pod network, I've lifted this from the Kubernetes documentation. Every pod in a cluster gets its own unique cluster-wide IP address. And the reason that's important is that it enables completely NAT-less communication within the cluster. As an application developer or someone who's run applications, one of the immediate benefits of that is that every application can listen on the same port without there ever being a risk of port clash. This communication can be IPv4, IPv6, or dual stack, and in the newest versions of Kubernetes, they're leaning towards dual stack by default for the pod network. The pod network is implemented by the container network interface, which is sometimes referred to as the, there's the diagram, sometimes referred to as the CNI. And basically all that does is it manipulates the route tables on the underlying nodes to enable the pods to talk to each other on this separate virtual network. Some of the CNIs add kind of extra features on top of the basic job that they're doing of giving every pod an IP address and enabling the routing. So, for example, Calico, which is the one I'm most familiar with, takes the native network policy objects that the Kubernetes brain or control plane accepts from users, and it allows us to use those to do very fine-grained ingress and egress control on that pod network. And I think that's everything about the pod network. Right, sorry, here's I've got out of sync with my notes. So here's just an arrow showing that pod in slightly darker blue can talk to the pod next to it on the adjacent node, and it does that directly. Of course, the traffic is actually routed via the underlying host network, thanks to what the container network interface does for us. So the other network that Kubernetes introduces is the service network. As I've alluded to, this is not really a network at all. As an operational engineer, one of our typical use cases is to make sure that my application can talk to its dependencies. And of course, we want those to be load balanced, and we don't really care which instance of our downstream dependency that any request gets routed to. So in this case, this is where the service network becomes important. So the service network is used to basically expose applications and services to other services, both within the cluster and without the cluster. So think about the internal networking first and then move on to the externals. So we've got 3 pods there in slightly darker blue. 2 of them are labeled foo. So our app is right, sorry, I've got some arrows now. I think the colors have changed at some point. So the basic principle here is that we've got a pod that wants to talk to a downstream service, and it's first of all it's going to be hard coded with, or it's going to be configured with a downstream DNS name. So in this case, service-foo, and within the cluster that's going to resolve to an IP address of the service network. The pod is going to connect to that IP and magically have its request routed via the host network to another pod. Completely invisible, transparent. The pod knows nothing about that. How does this work? This is run via an agent called the kube proxy. The kube proxy runs on every node in the cluster, and its job is to manipulate the IP tables so that IP address 10.0.0.2 is load balanced to other IP addresses within the pod network. It's completely transparent to the caller, and obviously there's an integration there with the cluster DNS provision as well, so that there's no hard coding of IP addresses. The requesting pod just asks for service foo. Once it's got the IP address via DNS, it connects with that IP, and that will be load balanced to somewhere else in the cluster. So that is the simplest type of service within the service network. It's referred to as the cluster IP. That's used for predominantly for internal communication, so service to service. It's TCP by default, but we can use UDP and SCTP as well. And there can be some limitations in the load balancing algorithms as well. So I mentioned IP tables. Newer kernels support IPVS, which has better load balancing options. But there are some limitations that you need to be aware of, especially if you're implementing this kind of network on open source Kubernetes, when you've got perhaps more control than you would do on one of the hyperscalers packaged versions of Kubernetes. But the service network can also be used for exposing services to the outside world, and so this is done via service of type node port. So here we've got, for example, 3 instances of pod foo, and they've got their references on the internal service network. But you'll see at the bottom here that we've also opened port 30,000 on the IP address, on the host IP, so on that host interface. And what that means is, in order to get to service foo from the outside world, we can hit one of the nodes where it's running on that on that port on IP, and the service network, that IP tables layer, is going to intercept that request and direct it to the running instance. So then you typically integrate this with an external load balancer. So here's a kind of end-to-end access example. We've got our customer coming in through some third-party load balancer. The request hits one of the nodes where that pod foo is running. It hits one of those nodes on that node port 30,000, and then the traffic is directed into the application. You'll also see that the left-handmost node is grayed out. So by default, the node ports only listen on the nodes where there actually has instances of that application running. Personally, I think this is simplest from a point of view of load balancing, because it means that the load balancing is being done by your external load balancer, but there is the option of also directing the traffic into a node where the pod is not running, and then the service network can intercept that traffic and direct it to a node where it is running. It's also worth noting that there's implications here for in terms of loss of client IP, although that will depend on whether that matters or not, will depend on what your application does with client IP. So just to give another end-to-end access example, a simple example is just to look at one of our service pods talking out to a database. And this is pretty simple, really. The traffic goes out via the host network and is subject to NAT. Unless you've integrated your CNI, that network interface with your wider network, in which case you can turn NAT off if that's desirable. So just one more slide, really. Kubernetes networking is extensible, it's flexible. I wouldn't say there's a huge amount of choice, but there are different networking plugins, different options in the CNI space. So, for example, some of them offer BGP peering, so you can actually advertise all of your pod IPs to your external network if that's desirable. So that means your pod network can actually stretch outside of the cluster. Some of them also implement network policies using either Kubernetes native objects or by using other extensions and metadata that you can add to your services, and some actually also include the possibility of doing that in a cross-cluster manner. You may be aware, just because of a security point of view, many organizations end up running multiple clusters with different security postures, and depending on whether they're internet-facing or database-facing, that kind of thing. And there's also the option of encapsulation, so whether it's VXLAN or other technologies to allow traffic to traverse across different VLANs, which may be necessary, for example, if you're running in the cloud and you need to run multi-region or I'm going to use AWS-specific terminology, multi-AZ, availability zone. So different network providers, network interface providers provide different levels of extensibility, different options there, depending on the kind of use case and requirements. And the Kubernetes also has the concept of controller, and a controller is basically a plugin that helps Kubernetes maintain state. So it comes with some built-in controllers. But for example, you can use controllers to manage your external appliances. So some controllers might allow you to manage an external load balancer or an external firewall. And they're also developing a gateway API, which is another method of connecting Kubernetes with the outside world in terms of physical networking devices. And because my notes weren't working, I forgot to say, because I've got a minute left, I'm going to flip back to this slide here. So I was mentioning about the node port and the idea of having an external load balancer. If you're running on Kubernetes Cloud, one of the cloud providers, you can also deploy a service of the type load balancer, and what that's going to do is, using that controller mechanism that I just mentioned, it's going to spin up a load balancer for you using the cloud provider's offerings and sort of expose those services automatically and maintain state. And they also do the same. Some of them do the same sort of thing from a firewall point of view. So maybe Kubernetes is good for security after all. And I will skip forward to Q&A slide. Thank you for your attention.
Thank you very much, James. Any questions in the room? Dave, any questions?
Thank you
very much.
Thanks.